we want to quickly walk through a few approaches that we've seen for handling this routing across multiple cluster types, and break down the overall architecture and also summarize some of the pros and cons we've seen for each of these approaches. So the first one that we've seen is probably the simplest of the approaches that we're going to see. So for each of these scenarios that we're going to talk through, the common situation that we're going to use is that we've got a couple of different clusters that are running somewhere. We're going to say one is a Kubernetes cluster, one's a Docker Swarm cluster, and each one of those has a couple of different services running. So for example, we've got service A and B in Kubernetes, service C and D in Docker Swarm. We've got an ingress running in each one of those that's handling incoming requests, proxying them back to the correct service based on some sort of logic. So that pattern within the clusters themselves has been pretty well established, and that is largely a solved problem. But outside of that, it can start to get more complex. So in this particular approach, the way that we've seen customers route across these different clusters is through simple DNS entries. So you've got a DNS provider that you are maintaining A or maybe C name records pointing to the addresses of these ingress instances for each of your clusters. So relatively straightforward. You've got a record for maybe cluster A.example.com routing to Kubernetes, cluster B.example.com routing to Docker Swarm. So the main benefit in this type of scenario is that it's relatively simple. There are fewer moving parts to have to deal with, to have to worry about maintaining the configuration. But there are a lot of challenges that are presented with this type of approach. So the main one is that it's kind of at odds with that cloud native ecosystem where a lot of times your IP addresses are dynamic. If they're in the container world, they're updating frequently. And updating those through DNS can be problematic, especially when you start to account for the lag that can be associated with those DNS entry updates. It runs into reliability issues for being able to quickly update your configuration and your routing. The other challenge that we see is that this will drive some design decisions for how you're routing across clusters. And namely, if you've got non-identical sets of services in these clusters. So like in the example we're looking at where we've got service A, service B in one, service C, service D in another, we're going to have to manually call out which router or which cluster rather we're routing to from that first layer router. So that's going to impact how we design our API endpoints as well. So let's go from there and look at another example. So in this case, we are using the same general framework. We've got the same routing strategy, but we've added an additional component here where rather than routing directly via DNS, we've got some sort of edge reverse proxy that is layered in front of these ingresses in the clusters themselves. So same logic is being applied. We've got cluster A and cluster B that we are routing based on the host name to these individual clusters. But the difference here is that we've now got this reverse proxy that is handling that, that is then being pointed to by most likely some sort of wildcard DNS entry to this proxy instance. So in this case, we have some benefits to the approach. The main one is compared with the previous approach, the changes are going to be more immediate than if we're trying to manipulate these updates through DNS entries. The other benefit is that this is a relatively simple configuration that we have to maintain at the this edge reverse proxy instance. So we've got a single line item of configuration for each of the clusters that are attached. But there's still some challenges. So we still have to use that grouped by cluster routing for our routing endpoints. So for that reason, we can't expose a single API endpoint like maybe api.example.com. And beyond that, the configuration still is manual. We're still going to have to maintain this both at the lower level and at this, this new edge reverse proxy level. So let's wrap up this section with a third scenario where we've got the exact same architecture that we were looking at before, where we've got DNS pointing to a reverse proxy at the edge that's then routing to the ingresses in each of the clusters. The difference here is rather than routing by the cluster name by host name, we are maintaining a list of each of the individual services and where they are currently located at the reverse proxy layer. So for example, we know that service A and service B are running in this Kubernetes cluster. We know service C and service D are running in this Docker Swarm cluster. So we've got those routing rules listed accordingly at the reverse proxy layer. So the main benefit to this approach, as compared to the other ones we've talked about, is that this allows for a more flexible approach to our routing across the clusters. And namely, that means that we don't have the same challenge and we can expose a single API endpoint, say api.example.com, to route to these multiple clusters. The challenges here, though, mainly stem from the fact that your configuration on this edge proxy layer starts to get pretty complex, especially if you are, operating at the scale of not a couple of services per cluster, but tens or hundreds. That can get very complex very quickly. That introduces a higher risk for configuration errors. If you've got to maintain what's running where at that edge proxy layer, that can get pretty risky pretty quickly. And finally, when you start to look at this in the context of some sort of migration activity, say from Swarm to Kubernetes, that requires a ton of planning that you're going to have to figure out both in the cluster itself and making sure that you're coordinating these routing rules across all layers of your infrastructure as well. Let's jump into this new feature and how it relates to everything we've been talking about so far in terms of the challenges and the existing solutions for multi-cluster routing. So this diagram that we're looking at is an example of how we can use a new feature called the Traefik Provider that's been introduced in version 2.5 of Traefik Enterprise. And basically what this allows us to do is to automate away a lot of those challenges that we just walked through for each of the existing solutions for this type of multi-cluster routing. And the way it works is that if we start to break down our original example framework for these multiple clusters. So if we have a couple of clusters, one Kubernetes, one Swarm. In Kubernetes, we have Traefik Enterprise running as the ingress controller in Kubernetes. It is talking to the Kubernetes API to do service discovery. In the Swarm cluster, same thing. We've got Traefik Enterprise running as the ingress for the Swarm cluster. It's talking to the Docker API to do service discovery there. And then we're also introducing this third layer of Traefik Enterprise that is running at the edge here in front of both of these clusters. And basically, rather than having to manually maintain that list of routing either by cluster or by service like we saw earlier, this Traefik Provider allows us to point to the API on each of these lower level clusters and automatically sync that dynamic configuration up to this first layer. So basically, once we set all that up, we're able to have this first layer of Traefik Enterprise automatically route incoming requests correctly to Kubernetes or to Swarm based on this underlying configuration without having to do any of that manual updates to the configuration on this first layer instance.